We understand how to solve an equation for its variable, and that's when we just had one equation that's in terms of one variable. We can solve for that variable to find out what value or values of that variable make the equation true. But what happens if you have two variables? So if you have two variables that you need to identify their solutions, you need to have two equations. And so that's where the system of linear equations is going to come into play in this section. And for the first section anyway, we're going to be looking at linear equations, and eventually we're going to expand this knowledge into nonlinear equations where the equations might represent a parabola or some other nonlinear function. But for now, we're just going to focus on linear equations. So there's a few different methods we could use to find the solution to these, to the system of linear equations. A system is just an accumulation of more than one equation. So if you have two variables, you need to have two equations. If you ever have three variables, you need to have three equations. And so that would mean your system of equations involves three equations. So the number of variables you have represents how many equations you need to solve for those variables. So when we're solving a system of linear equations, we could come up with a few different scenarios. One is where you just get one solution. And so in a case of two variables that would be graphed in two-dimensional space, maybe just x and y, that would be if the two equations, the graphs of the two equations intersected, and the point of intersection is going to represent your solution. In the case of three variables, you're talking three-dimensional space, and so that would be a plane. Two or more planes are intersecting, and one location, and that's what you would get for your solution. So it's the point of intersection. In the second case, we're talking about no solution. So this could also happen where you have a system of equations and unfortunately you have no solution, no values of x and y that make both equations true. So in that situation, you're going to have the graphs of two lines that might be parallel, and those parallel lines will never intersect. And then the third situation is where you have an infinite number of solutions. So once again, in the case of two variables, so in two-dimensional space, you might have a line that would represent, that's the graph of one of your equations. And then the second equation would have a graph that's exactly the same line. And so those two lines are on top of one another, which represents an infinite number of solutions. And you're going to see examples of all three of these when we go through these examples, so you understand how to interpret your answers. And so the first method, or one of the methods we're going to use to solve our system of equations is using substitution. Substitution is great because you can use this method even if your equations are nonlinear. Elimination is useful for the same reason. So you're going to have to decide which of these two methods are more convenient for you. And then the third method, which is only going to be useful to you if you have use of technology. So graphing these equations and actually having the calculator or the technology find that point of intersection is another way you could figure out your solution to your system. So we're going to focus mostly on the first two methods, the substitution and the elimination, also sometimes called the addition method. So you have to look at your system of equations and decide whether you want to use substitution or elimination. So here's what you're looking for. If one of your equations is already solved for a variable, if it already has x equals some expression or y equals some expression, I would probably use substitution in that case. All right, and so you're going to see an example shortly where that would be appropriate. This example is not set up that way. For number 20, we have two equations where the x and the y terms are on the left side of the equal sign and then the constant on the right. When it's in that setup, I prefer to use the elimination method or the addition method. So what you're going to do is make sure that your like terms are lined up from top to bottom. X's with X's, Y's on Y's, and then equal signs, and then the constants. Has to be in the same order for both equations for this method to work. So I'm using the elimination method on this example. What you want to do now is add your like terms together. And when you add the like terms together, X's and X's, Y's to Y's, constant to constant, one of your variables is going to cancel out, which means you're going to get a sum of 0. So when I add 1x to 2x, I get 3x. That did not eliminate. When I add 3y to negative 3y, I do get 0. And so the y variable was eliminated. So I'm going to write this out for you so you can understand exactly how this is operating. So x plus 3y equals 5, and 2x minus 3y equals negative 8. And so there's my equal sign, right, where I'm going to be adding my like terms together from top to bottom. So we get 3x, we get 0y, so let's just leave that off, equals 5 and negative 8 gives you negative 3. Now we have an equation with just x. We can solve for that x. We get -1. Once you know the value for one of your variables, you're going to substitute that back into either of your equations from the beginning to find the other variable. So you choose whichever equation is the easier one. I like the first one because it has less to do. And so I'm going to write the equation down that I'm going to be using right now. And then I'm going to substitute the value -1 in place of the x. And this is going to give me an equation with just y. So 3y is equal to 6, so y is equal to 2. So you're going to write your solution as an ordered pair. The ordered pair is going to be the point -1, comma, 2. -1, 2 is the ordered pair that makes the system of equations true, which means if I plugged in -1 for x and 2 for y into both equations, I would get a true statement. These two lines intersect at the point -1, 2. So that is my one and only solution. Next example looks pretty similar. You might notice that if you were to add your like terms straight away, you're not going to get anything that cancels. Whoops. So I'm just going to recopy it as it appears, and then we're going to decide how to handle this. Okay, so like I said, if you add the x's, I don't get 0. If you add the y's, you don't get 0. So that's a problem. You need to adjust one or both equations by multiplying through by a particular factor. The factor that you use is something that's convenient, that's going to cause one of your variables to be eliminated. That would give you a 0 sum when you add its like term to it. So if you want to eliminate the x term, you might choose multiplying the entire equation by 3, because that's going to give you a positive 3x on top and a negative 3x on the bottom, and you'll see that the x terms cancel out. Now those of you who are thinking ahead are going to notice the issue that we're going to have to deal with. Oh, you know what? I made a mistake. I'm glad I made that mistake. You have to multiply the entire equation by the 3, not just the x's and the y's. So that actually gives me a 15. All right, so go ahead and add those like terms together. You get 0x plus 0y, see there's the dilemma, equals 17. So what you need to do now is decide if that is actually a true or a false statement. All of my variables were eliminated, both the x's and the y's. In other words, 0 is equal to 17 is what you would have written down maybe. And you have to decide, is that true or false? Well, that is obviously false. 0 does not equal 17, and therefore you have no solution. These two lines that you see here, the equations of these two lines are going to be they're going to be parallel lines, right? They do not intersect at all. They're parallel lines. And so how do you write your answer? Well, you're going to tell me that there's an infinite number of solutions. Oh, sorry, that didn't make any sense, did it? There's no solution. Sorry about that. There's no solution. And so, yeah, that's all you got to say. Nothing is happening. Parallel lines. Lines are parallel. And so when you're working through your homework online, you're going to see 3 different button options for your answers on these types of problems. The first button is going to say, yes, there's a solution and here's what it is, and you type in the ordered pair. The second button might say, there's an infinite number of solutions and here's what they look like. And then the third button might say there's no solution. And so you just want to make sure you hit that third option if that's the option that says there's no solution. All right, so let's move on to number 30. We're going to solve this using the elimination method again. Let's recopy our system so we have some room to work. 3x minus y equals 7. 9x minus 3y equals 21. We want one of the variables to be eliminated, to cancel out, give us a 0 sum. Maybe you choose multiplying the top equation through by a -3. -3. And so I'm looking at the y's in this case. I'm looking at getting a positive 3y on top to combine with a negative 3y underneath, and that'll give me a 0. But once again, those of you who are looking ahead might see what's going to be happening. Okay, go ahead and add your like terms together. You get zeros on the left and you get a 0 on the right. Everything's gone. Everything was eliminated. And now you have to look at what's left. Since your variables are gone, you have to decide if that equation that you have in the end is true or false. That is actually true. Yeah, 0 does equal 0. And so you have an infinite number of solutions. infinitely many solutions. And so we have to decide how to write these solutions because they exist. We just have to decide what form they're going to take on. So if you think about what's happening with the graphs of these two lines, they're going to be the same line. Equations represent the same line. Okay, so they just differ from one another by a factor of 3 in this case, right? And so the way you're going to write your solutions, you're going to say your answer is all pairs of x, y, so all ordered pairs. And I do believe that MLP is going to set you up with this particular template such that, now here's what you have to do. You could write in such that they take on the form 3x minus y equals 7. That should be acceptable. Or you could have said they take on the form y equals 3x minus 7. And you understand how to get that just by moving the y to the opposite side and then the 7 to be with the 3x. And so these two equations are equivalent to one another. And so I prefer to write it with the variable y by itself just because it makes a little bit more sense to me. I can see instantly from that form that this is going to be the line that hits the y-axis at -7 and has a positive slope. So all of my ordered pairs are going to be on that line. So play around with the MyLabs Plus program just to see what types of answers are permissible. All right, example 44 now is a little bit more complicated because now I have 3 variables. I have x, y, and z. And so now I'm not talking about 2-dimensional space. I'm talking about 3-dimensional space. Instead of lines intersecting, I have planes that are intersecting. And I like to think of planes as a visual. I like to represent the planes by maybe the walls in your room and maybe the ceiling or the floor. And so if you consider 2 adjacent walls and wherever you are right now, 2 adjacent walls that meet on an edge, and then maybe take those 2 walls and intersect them with the ceiling, let's say. And so the point of intersection for all 3 of those planes would be that point in the top corner of your room. And that's my visual aid for 3-dimensional planes. So the way we solve the system of 3 equations and 3 unknowns is pretty similar. You can decide if elimination is the way to go. If I look at the equations, let's see, and be prepared to try something and have it not work and then try something different. You're not going to always get it right the first time through. But let me think. If I take the first 2 equations, let's start with those. Okay, 2x plus y minus 3z equals 6. And when I write out my next equation, I'm going to space things out so that the like terms are in the appropriate positions. Makes it a little bit easier to see. Solving using elimination, let's say, if I want one of my variables to be eliminated, you might consider multiplying the second equation by -1. And that's going to leave you with 2x plus y minus 3z is equal to 6, and -2x plus 3z is equal to -16. And then you might add your like terms together, right? So we end up getting y is equal to -10. Y is equal to -10. And that was very convenient. That was a great idea because then I just figured out the solution for my y variable. Great. I'm 1/3 of the way there. I need to find x and I need to find z. Well, if we know that y is equal to 10, look over at your system of equations. And did you notice that the third equation only involves y and z? So let's go ahead and substitute the value -10 in place of that y. So 2 times -10 is -20 plus z is equal to 4. And that's going to give you z is equal to 24. Now you know y and you know z. To find x, use those values, plug them back into any of your equations, and that also involve x, and that will allow you to figure out the solution for x. So the second equation had x and z. So if I substitute 24 in place of the z, I get, what is it, 3 times 24, 72 equals 16. And then add that 72 to the other side. So 2x equals, okay, 88. How about that? That looks right. And so that means that x is equal to 44. And now you know your solution. You have one solution to the system of equations. We're going to write this as an ordered triple because there are three components, the x component, then the y, and then the z. So we put those in the order of x, y, z. All right, now that we understand how to solve systems of equations, we are going to look at some applications. Actually, this might be a great time for a break. Let's take a break.